All right. So, hello everyone, and welcome to McLean 360. I'm excited to see you here once again. And we are looking at a simply supported beam, which is having a uniformly distributed load, or what we normally call a UDL, right? And then we have a concentrated moment. So let's read the problem together and solve it. Okay. So over here we've got a horizontal beam, and this horizontal beam is freely supported at A and B, which is 8 meters apart, and then it carries a uniformly distributed load, which is sort of a UDL, all right, a UDL of 15 kilonewton per meter, which is running, and then including its own weight, right? So it spans across the entire length. And then there is a clockwise moment, so that's what I was calling the concentrated moment, okay? Concentrated moment. And this concentrated moment is actually at the point C here, right here. And then he's saying that, which is 3 meters from the left hand support A. Now our task is to calculate the slope of the beam at C, and you have been given the flexural rigidity. So EI is called flexural rigidity. And sometimes it is called the stiffness, okay? Sometimes it is called the stiffness or the flexural rigidity. Right, let's go ahead and solve this problem. The first thing that you have to understand is that whenever you are given a question like this, the first step is to look at the statics, okay? So statics, and what is statics here? First of all, solve for the reaction at the support. So reactions at the support. Let's quickly do that. Reactions at the support. Now, how can I find the reaction at the support? So I'm going to assume that there is RA, which is a kind of reaction at A here. And then there is RB, which is the reaction at the support B here. Okay. But how will I be able to get the reactions? The first thing that you have to, the next thing you have to look at is that whenever you have a UDL behaves like a rectangle, okay? So if you have a rectangle, the area of a rectangle is given by the length times the breadth, okay? And then, so in this case, the length is actually that span, okay? So the length is the span, which is 8 meters span, okay? So that 8 meter span is the length. And then the weight, in this case, is the intensity, okay? Or the distribution, which is actually given by 15 kilonewton per meter. That is to say, the actual weight or the actual load is nothing but the area, which is given by 15 multiplied by 8, and this will give you the actual load, okay? And so if you multiply 15 by 8, that will give us the actual distribution, and 15 by 8 is going to give us what? 120. Now this 120 that you have gotten is not necessarily the area, but then it is actually in terms of the deflection of beams, it is actually the single load, and this single load will act at a certain distance, okay? So maybe let me change the color. This single load will act at a distance somewhere here, which is going to be at the center, okay? So that load is going to be 120 kilonewton, and then it will act at the center, okay? So that means the distance from that point to where, or let's say halfway, so that is 4, and the rest will also be 4. So this is the first thing that you have to do. Now let's go back to statics and then find the support reaction. So we are going to assume that this body is in equilibrium, and for rigid body to be in equilibrium, number one, summation of forces positive in the y direction should be 0. So we can see that RA minus 120, because it's coming down, plus RB should be 0. In other words, we can say that RA plus RB is equal to 120. So let's call this equation 1, okay? Once that we have gotten equation 1, now the next step is to look at the moment, okay? So for a rigid body to be in equilibrium, summation of forces and moment, so we say that clockwise is positive, should be equal to 0. Let's take moment about, say, point A. Taking moment about point A, so we are taking moment about point A. Don't forget that the concentrated moment at C is already applied on the beam itself. So that one is already there. So we will bring that one 160 because it's positive, because it's clockwise positive. And then you realize that this one 160 clockwise, and then if you look at the 120 kilonewton load, the load is acting at the center. Okay, that means if I take moment, then the distance that I'm going to use for the moment will be what? Exactly halfway, which is what? 4 meters. I hope you are not confused, because we said the load will act at the center. So that moment will cause it in the direction of this direction, which is clockwise. Okay, so that one will also be positive. So therefore, it's going to be plus 120 multiplied by 4. And finally, the reaction RB here is going to have a moment which is going to go what? Counterclockwise, because it's going to go in that sense. Yeah. And so it's actually going to be minus 8 RB. And then is there any other moment? No. So now solving for the moment, let's add everything up. So we have 160 and then plus 120 and then multiply by 4. And what do we get for this? So we get 640. All right. So that is it. You get 640. Okay. Yeah, so 640. So that is when you do everything should be equal to what? 8 RB. In other words, you can say that RB is what? 640 divided by 8. And what is 640 divided by 8? Essentially, 640 divided by 8 is nothing but what? 80. It means that RB is 80 newtons. That's all. So if RB is 80 newtons, then we can confidently say RA is what? 120 minus RB. And that will give us what? So 120 minus 80, and that is 40 kilonewton. Sorry. This one is also going to be kilonewton. Now you see that RA and RB has been solved. But then that is the first step. So if you do up to this point, you have not done anything, because you did all of this in your statics class. So it is assumed that you already know all of this. Okay. So now I can clean RA and RB. Then I will now move to the strength of materials part, which is what? The deflection, because now I'm done with the statics part. Right. Now, before you can be able to find the deflection, or let's say the slope, but then I will also do the deflection as well. We are going to use Macaulay's principle. Now, Macaulay's principle is saying that cut anywhere of the beam. Okay. Cut anywhere of the beam, or take a section. And then, so it means that we can stand, let's say at this point, and take a section. Okay. Let me use another color so that you can get it well. So let's say we stand somewhere and take a section. Okay. Let's call it section XX. Okay. So we have taken that section. Now let me draw the section quickly, and I'll show you how to deal with problems like this. And I think that is the best way you can actually look at it. Okay, so I'm going to draw the section. Sorry. Okay, good. So this is the section that I was talking about. Now, interestingly, what we are trying to say is that we have taken a portion of the beam, okay, and we are calling that portion of the beam X, where X is 0 at this point. X is 0 until we get to X equals X, and at the end of the beam, X will be equal to L. That's all. Now, interestingly, because this is a uniformly distributed load, it means that even if I take a portion, the portion will still be behaving as what? A uniform distributed load. So if the original design, you see that when we started, we multiplied the intensity by the length, right? How we were able to get the 120. So this time around, and it acted at the center. This time around, the uniform distributed load here, we don't know, because we have taken a portion. So we assume that if the uniform distributed load is, let's say, so if the load is varying and the varying load intensity is, say, 15 kilonewton per meter, then it will also be varying here as well. Okay, it will also be varying here as well. But then if you want to represent this one too by one single force, then that single force will be equivalent to what? Multiplying this time the 15 by what? X. Okay, so this time around it will be 15 by what? The X. So that is basically what we are saying. I hope it makes sense. So 15 kilonewton multiplied by X, and that distance is going to be what? 1/2 of X. So in other words, it's going to be X over 2, right? I hope I have not confused you yet All what we are trying to say is that a uniform distributed load will always act at the center, and then it will take the magnitude of what? The span, which is the length, in this case x, multiplied by the load, which is what? 15. That is the uniform distributed load, right? After doing this, there is a convention here. Please take notice of this. Whenever you cut at this side, shear force is positive downwards, and then moment is in this direction. This is like a sort of convention, right? Now let's quickly go through this. So all what we are trying to do is that we want to come up with a moment about this x. So let's say that this beam is in equilibrium, therefore summation of moment about section x will be 0. And then we are going to assume that clockwise is positive. Okay, so clockwise is positive, and we are summing moment about the section x to be equal to 0. So first of all, there is mx, and that mx is actually the moment because of the cutting. Okay, so we call it the internal moment. So it's going to be m of x, and then we are assuming clockwise is positive, and then m of x is going that way, so it is going to be negated. Okay, so m of x is going to be negative, right? And then we have 160 kilonewtons, but that one is going clockwise, so it's going to be plus. So 160,000. Okay, let's do it that way. But then who can tell us the moment? Now this is where you have to begin to understand strength of materials very well. You see that the point which is called the C is at a distance 3 meters. Okay, what this means is that if from A to C is 3, and from A to B from A to X is X, then it means this small distance here, what is the distance? What do you think? If from here to here is 3, and then the long one is X, then probably, or not probably, then actually this one is x minus 3. So it means for that moment, we are going to use x minus 3. But the trick is that it is already moment. So since we are summing moment and this is already moment, we will rather say x minus 3 and we'll put 0 here. So this is the trick. Whenever you are dealing with Macaulay's principle and you have a concentrated moment, you do the first time, the moment time the distance, but you intentionally put 0 here. The idea is that 0 is actually 1. Anything raised to the power 0 is 1, but we are just putting it there so that we can do the integration. Okay, now look at this force here, which is the 15,000 x. You see that it is going to come in the counterclockwise direction. Okay, so it's going to be minus 15,000. Okay, so minus 15,000, and then the distance is going to be what? So the distance is going to be, so 15,000 x multiplied by x over 2. Please pay attention. You see that the 15,000 x is coming from the fact that it was a uniform distributed load, right? So we multiply the magnitude of 15 by what? The span, right? We multiply the intensity by the span, and then it is acting halfway of x, which is like x over 2, right? So we are done with that part. Sorry. Now, is there any other moment that we have not looked at? Yes, you see that the 40 here, it is also causing a movement, but that one too will be clockwise. So plus, in fact, that was the first one, but anyway, we can just do it like that. So 40,000 into what? X. That one is straightforward. 40,000 into x. Don't forget, we are taking moment about x's. Now I think we have taken all the moments and we are done. So we can equate this to 0. Okay, right. So at this point, we will just say that m of x, which is our moment function, or what we call the singularity function, is nothing but what? So you can rearrange this, because m of x is coming here to become positive. Everything else will remain. So I can just say that 40,000, so 40,000 x, right? And then I'll say that plus 160,000 x minus 3 to the power 0, and then minus what? So 15,000 divided by 2 it will give us what? So 15,000 divided by 2, that is 7,500, isn't it? So 7,500, and then x times x is what? X squared. And then this is actually our moment function. Please, if there is any question up to this point, kindly drop it in the comment section. Okay, so now what are we trying to achieve? All what we want to do is that the moment function and the deflection of the beam is saying that if I have the moment function, it is equal to EI d squared y dx squared. So the whole idea is that we want to use the double integration to be able to find the slope or the deflection, right? But now that we have the moment, we will just equate the moment to whatever we have here. So then we can write that EI d squared y dx squared will be whatever is here, and basically that is going to be what? So we have 40,000 x plus what? 160,000 x minus 3 0, and then minus what? 7,500 x squared. So at this point, if you want to get the slope, you integrate. Okay, so let's do integration. So at this point, the strength of materials, we are done. All what we are coming to do right now is boundary value problem. Okay, so this is now a boundary value differential equation, right? So let's integrate this function with respect to x. So integrate with respect to x. Let's do that. So if I integrate, I will get what? ei dy dx, right? But please, when you get to the integration, deal with the variables and leave the constant. So for instance, 40,000 will stay here. If you integrate x, you get x squared over 2, and then plus you have 160,000. But you see that this one, it is 0, so you add 1 here, which is the same as just making it 1. That's all. If you divide by 1, the same thing. Then when you come here, minus 7,500, and then integrate x squared, you get what? X cubed over 3. Okay, but whenever you do integration, you need to bring a constant, so plus c1. Make sense? Good. Now you do the integration again so that you can get what? You do the integration again so that you can get the other constant. So integrate again with respect to what? X. Let's do that again. So if I integrate the slope, I get the deflection, which is equal to what? Now this time around, it's going to be what? So 40,000 divided by 2 is 20,000, right? So then 20,000, now you are going to integrate x squared, so it's going to be x cubed over 3, isn't it? And then plus what? This time around is going to be 160,000, and then what? x2. So if you put 2 here, then it means you have to divide here 2 by 2, right? We didn't divide here because it was just 1, okay? So you add by 1 and divide by the new power. Now again, we are going to do 7,500 divided by 3. I know this is divisible, but let's just maintain it like that. And then let's integrate x cubed. So it's going to be x to the power 4 divided by 4. So all the time, shift the variables and the constant to one side. Don't do it together. It will confuse you. Plus c1 times x, which is like integrating a constant with respect to x. Then another c2, right? Because you have done the integration. Now let's look at the boundary value. So boundary conditions. Now, whenever you have a simply supported beam, the boundary conditions are such that all the time for a simply supported beam, at s equals 0, the deflection is 0. And then at s equals L, still the deflection is 0. So all what we are trying to say is that whenever you have a beam which is a simply supported beam, the deflection at the ends are always 0. All the time. Always. For a simply supported beam. Okay. So now coming back to our question, it means that if we put s equals 0, we expect that y to be also 0, right? So 0 will be 0 plus 0 minus 0 plus 0 plus what? C2, which is telling us that C2 must be what? 0. Simple and straightforward. So C2 is 0. We are done with that aspect. Okay, good. Now let's come to this part, which is saying that we should calculate C1. Okay, so we are done with C2. So we will rather put x equals the length, which is L, and then we will equate it to what? Y to 0. So let's do it together. So 0 is equal to, but don't forget that the length is what? So the length is actually okay, by the way, let me write the deflection equation all again proper. Okay, let me write the deflection equation proper. So 20,000 divided by 3. So 20,000 divided by 3, which is 6,000. So we have 666.67 x cubed plus, I think 160,000 will be what? 80,000, right? Okay, so that you'll be happy, let me do it for you. So we have 160,000 divided by 2, 80,000, right? And then finally if I have 7,500, so 7,500 divided by 12, which is 4 multiplied by 3, that is 625. So minus what? 625 x to the power 4 plus c1x. c2 is 0, so we don't need to bother. Right, so at this point we are going to say that when y is 0, x is L, so 666.67, the length is actually 8 plus 80,000, and then 8 minus 3 squared minus 625, 8 to the power 4 plus 8c1. So at this point, this is just algebra, okay? You just have to put everything together. Now let's do it together. So it's going to be 6666.67 multiplied by 8, and then raised to the power 3, and then we've got plus, so 80,000 multiplied by what? 8 minus 3 is 5, so 5 squared, and then minus what? 625 multiplied by what? 8, and then raised to the power what? 4. Right, so everything here will give us 285,3335.04, isn't it? So 228, so we have 285,33, so the 3 is 3, 5.04 plus what? 8c1. So at this juncture, I expect you to know how to do this. So c1 will be minus what? 285,335.04 all divided by what? 8. So that is c1. So if you divide this by 8, but I don't recommend you to be using answer because you may not know what is at the variable answer, but I assume that we all know the answer already. So minus 35,6666, so the 6 is 4.88. Okay, so this is the value of c1, which means that we can now go ahead and write the deflection equation because we now know the c1, which is here, sorry, the slope. It means that our slope equation our slope equation dy dx is nothing but so our slope equation is going to be what? So we are just going to copy and paste everything again. So this is the slope equation. It's going to be 40,000 divided by 2, which is 20,000. So we have 20,000 x squared. Okay, so if you do the 20,000 x squared, then we come to what? 160,000 divided by 2, which is what? 80,000. So so actually it's going to be, sorry, yeah, so 80,000 x minus 3, so plus 80,000 x minus 3, okay, I think here is 1, and then finally minus so actually if you do this one, sorry, I think we are dealing with the slope. So for the slope, sorry about that, for the slope, this is actually going to be, oh, sorry about that, we just messed up everything. So let's do the slope. Sorry, you know, we are dealing with figures, so sometimes we can make mistake, and I am happy that you are watching and you see that there is a mistake so that it will prompt you to go back again. Right, so the slope is actually 20,000 x squared, so 20,000 x squared, and then what? Plus 160,000, so 160,000 x minus 3, and then minus what? 7,500 divided by 3 x cubed, so minus 7,500 divided by 3, and what is that? 7,500 divided by 3, 2,500. S cube plus C1, but we know C1 is what? 35,666.88, isn't it? So now if we want the slope at the point C, that means x equals 3. So all what you have to do is to just simply substitute s equals 3, which is very easy, because it's going to be 20,000 3 squared plus 16,000 3 minus 3, which is 0, minus 2,500 3 cube minus 35,666.88, isn't it? So whatever you get from here, then you divide it, the whole of this, you divide it by the EI, which was 40 times 10 to the power 3 kilonewton. So again, 10 to the power 3. Now I promise you that if you do it correct, the slope will be given so if you do it correct, the slope is going to be minus 6.104 times 10 minus 3 radian. But because of time, I want you to calculate it and do it. Now, if you want to calculate the deflection, or if you're interested in the deflection, you are just going to use this simple equation right here, okay? You are just going to use this simple equation. And then at s equals 3, you just put s equals 3 here. Already this part is going to be 0 for x equals 3, okay, for the deflection. So you see that it's going to be simple. I want you to solve for the deflection and give me the answer in the comment section. Thank you very much for watching.